An effective safety program requires an institutional commitment to health and safety and adequate resources, as well as institution, faculty, and individual accountability. Select the images to learn more.
A healthy safety culture exists when the importance of ensuring the safety of individuals, public health, and the environment is equal to and as important as the scientific outcomes. Good science is always safe science. Characteristics of a positive safety culture include these elements. All levels of the institution express a visible commitment to health and safety. Safety information, training, and services are readily available. Laboratory facilities are properly maintained, repaired, and renewed. Personal protective equipment is largely standardized and easy to obtain and replace. Individuals are encouraged to report issues and concerns without fear of blame, criticism, or resentment. Good catch or near-miss reporting of safety issues is actively encouraged and lessons learned are shared widely. The commitment to safety is a significant factor in evaluation. Safety is a consistent demonstrated value in all day-to-day activities. Problems are seen as opportunities for improvement. Safety, like good science, thrives in an environment of open discussion, attention to detail, careful planning, and forethought to potential catastrophic outcomes. A healthy safety culture exists in institutions that set high standards and provide the necessary resources and services to help scientists work safely. Training and education, like this course, help promote, sustain, and improve safety knowledge.
You have the right to know about the hazards in your lab space. Additionally, your institution, department, and principal investigator are responsible for providing training and information that is specific to the unique hazards in your lab and outlining the procedures you must follow. You have an obligation to participate in training on how to identify hazards and control risks. Follow your institution's laboratory safety policies and procedures. Select the images to learn more.
Independent of title or position, scientists are entitled to a properly designed, equipped, and maintained facility, safety training, assistance in the proper management and disposal of biological, chemical, and radioactive waste, appropriate personal protective equipment, first aid and medical services, information and periodic drills and/or reminders concerning emergency response. Your rights to report unsafe acts or conditions to your university or H&S department or the government without fear of retaliation. To request and receive workplace health and safety evaluations of your laboratory. To be informed of conditions or situations beyond your immediate control that may impact your work environment. For more information of your health and safety workers' rights, visit www.dir.ca.gov. Your responsibilities. Review and follow the health and safety policies of your institution. Participate in all required and suggested safety training programs. Dress appropriately, wear protective equipment, and keep your laboratory clean and organized. Model good laboratory practice and hold others accountable for the same. Within your ability and authority, correct unsafe acts or conditions immediately. Clean up spills, disconnect damaged equipment, label items out of service. Make service requests. Inform support personnel. Immediately report unsafe acts or conditions that are beyond your ability or authority to correct to your supervisor and safety program. Participate in evacuation drills and training events. Act quickly and decisively in an actual emergency, including calling 911 and evacuating the building.
There are very real and present dangers in laboratory science. Underestimation, complacency, neglect in identifying potential hazards, and failure to implement adequate controls of potential risks can have serious, sometimes fatal consequences. Please keep in mind the three major factors in laboratory incidents: They are inexperience, lack of planning and risk assessment, and a lack of proper oversight by the principal investigator or PI. Inexperience includes both your own inexperience and that of new members in your lab. Introducing a new procedure or technique often means that most individuals in the lab are inexperienced. A well-planned experiment that includes the identification of all hazards and assessing their risks helps to minimize the potential for incidents or lessens the severity of a negative outcome should an incident occur. A lack of oversight by the PI can be overcome by more frequent visits to the lab, modeling proper lab attire and practice when in the lab, and most importantly, making safety the first and last topic discussed at every laboratory meeting. The Safety Training Consortium recommends the PI Responsibilities course for every principal investigator of a teaching or research lab. Safety requires the commitment, leadership, and accountability of everyone working together in the laboratory. Human behavior is shaped by individual and community perceptions of hazard and risk. In situations such as starting a new experiment, the hazards and risks may sometimes not be obvious. Risk assessment is a concept that helps identify potential hazards and control the risks. The goal of risk assessment is to minimize exposure to you, others, and the environment. There is no single best risk assessment model. The suggested model in this course was developed for laboratory research and consists of 9 elements. It may be useful to reorder the elements depending on your individual needs. 1. Identify the primary hazard or obvious hazard, whether that is biological, chemical, radiological, or physical. 2. Recognize any secondary hazards. These hazards could include the end product of a chemical reaction or an inexperienced student who does not yet know the procedure well. 3. Outline the consequences of a failure: injury, exposure, illness, fire, explosion, etc. Ask yourself, how can I be injured and how seriously? 4. Define the routes of entry into the body: inhalation, ocular, ingestion, or contact with unprotected skin. Next, ask yourself, what can I do to prevent injury? 5. Recognize signs and symptoms of exposure: immediate, delayed, or cumulative. 6. Incorporate the available methods of control. For example, laboratory fume hoods, biological safety cabinets, shielding, pressure relief devices, and automatic controls. 7. Select the correct personal protective equipment, PPE, or proper dress for the lab, such as lab coat, eye and face protection, and the right hand protection. 8. Plan for an emergency. Know what procedures to follow, who to call, and the necessary supplies to have on hand. 9. Lastly, determine if the proposed work requires a form of prior approval by the institution. Write down key points of your risk assessment in your lab notebook. This helps you to be mindful of the hazard and reminds you to have all protective measures in place. A well-done risk assessment does not mean the proposed work is reasonably safe or the potential risks are understood and properly managed. A risk assessment helps you to choose the proper workspace and PPE. It can also help you to decide when the risk to conduct the experiment safely is too great for you. When in doubt, ask for experienced help and review by your PI before proceeding. Weigh the risks against the potential rewards.
True or false? Risk assessment is a concept that helps identify potential hazards and control risks. True or false? An effective mindset towards safety is proactive rather than reactive.
Hazardous materials may enter the body through primary routes of entry. Select each item to learn more.
Inhalation. This is the most direct and immediate route of entry into the body. Inhalation may occur when chemicals are opened and handled outside of a laboratory fume hood. Always handle hazardous chemicals inside a certified, properly functioning laboratory fume hood. Eyes and other mucous membranes. There are many substances that, if they enter the eyes, pose a serious risk of injury. Always wear approved eye protection. Eyes are the most vulnerable route of entry. Ingestion. This may occur from hand-to-mouth contact, poor hand washing practices, or the consumption of food and drink in lab spaces. In a well-managed laboratory, ingestion should always be the least likely route of entry. Absorption. Left unprotected, contact with the skin represents the most likely route of entry into the body in a laboratory. Proper dress, a lab coat, proper gloves, and good hand washing practices all help protect the skin. Good housekeeping, including the routine cleaning of common laboratory surfaces, helps prevent contact with contaminated surfaces. Injection. Injection may occur through mishaps with syringe needles or through accidents with broken glassware or other sharp objects that have been contaminated with chemicals. If accidental injection has occurred, wash the area with soap and water and seek medical attention if necessary. Cautious use of any sharp object is always critical.
Never underestimate the risk of working with hazardous materials, whether physical, biological, chemical, or radioactive. Specific hazards will be discussed throughout this course. An immediate, painful, and unmistakable outcome comes with exposure to strong acids or bases. In other cases, harm may accrue over a working lifetime through poor work practices, insidious or occult exposures, inadequate protective equipment, or limited safety information. Simply stated, you may not experience any adverse signs or symptoms immediately. As part of the risk assessment process, read all container labels and refer to the safety data sheets and other authoritative references for each material you will use. Minimize all exposures to hazardous chemicals through careful planning, the use of laboratory fume hoods, appropriate personal protective equipment, and meticulous personal hygiene. Most importantly of all, if you have concerns, experience discomfort, or develop any health-related concern, seek immediate medical care, inform your supervisor, file an incident report, and contact your safety program as soon as practical. For issues that are not acute or may simply be worrisome to you, ask for a medical consultation or follow up on these recommendations when speaking to your safety program. Laboratories and the workspaces within are considered designated areas for hazardous materials, equipment, and processes. The fundamentals of good health and hygiene include: laboratory water is not intended for human consumption. Never wash dishes, cups, or eating utensils in the laboratory. Avoid ingestion. Eat outside the lab and after washing your hands. Also, never store food or beverages in research areas. Always apply cosmetics, handle contact lenses, and take medications outside of the lab. Never smell or taste items in the lab. Finally, wash your hands often, specifically after removing your gloves. Images to learn more.
Good housekeeping is an important indicator in assessing laboratory safety. Some of the best housekeeping practices include: keep entrances, exits, and aisleways free of clutter and tripping hazards, clean up water, ice, and other spills on the floor, restrain all gas cylinders properly against a solid wall or permanent benchwork, use a self-locking stepladder to safely place and remove items from above. Maintain at least 18 inches of clearance in all directions around overhead sprinkler heads and smoke detectors, as well as room heating and cooling systems. Never place objects on those heating or cooling systems. Store coats, jackets, and other garments outside the lab. Secure personal items in a locked desk drawer. Remove and recycle packing materials as soon as items are received. Store lightweight and infrequently used items on upper shelves. Maintain at least 18 inches of clearance around eyewash stations and safety showers. Test your eyewash station frequently and allow the unit to run for 3 to 5 minutes to flush sediment and microorganisms from the device and its water line. Label and dispose of or repair damaged, broken, or obsolete equipment. Schedule periodic lab cleanup days. Routinely wipe down common lab surfaces with a dedicated sponge and a spray bottle filled with a mild laboratory detergent. Establish a procedure to ensure that those leaving your lab are required to thoroughly clean up their space before they graduate or receive their last paycheck. True or false? Ensure at least 18 inches of clearance around fire sprinklers, safety showers, eyewash units, and ventilation systems.
Children and minors are not permitted in areas where hazardous materials are stored, handled, or disposed of unless specifically permitted as part of an approved event or supervised research experience. Your institution should have a policy on special visitors and minors in the lab. Find out and follow what is required. Check the reference section for examples. Personal pets, such as dogs, must not be permitted in research areas. Service animals are an exception, but discuss this with your safety program first. The proper labeling, segregation, and storage of hazardous materials are important components of laboratory safety. Select to learn more about the proper storage of hazardous materials.
Segregate and label all hazardous materials by their primary hazard classification: biological, chemical, and radiological. Place all sharps, broken glass, razor blades, or needles into designated sharps containers. Separate according to their hazard classification. Buy no more chemicals than you will use in the next 3 to 6 months. Resist the temptation to stock up. Disposal cost is inevitably more than purchase price. Double date your containers to include date received and date opened. Dispose of time-sensitive materials before they expire. Segregate all hazardous chemicals according to their chemical class. Example, don't commingle acids and bases, flammables and oxidizers, etc. Store liquid hazardous chemicals in secondary containers to contain leaks and spills. Store all hazardous materials below eye level, avoiding the need to overextend or climb to reach containers. Store hazardous chemicals inside cabinets with doors and keep chemical containers off the floor. Use shelves with raised lips to help prevent items from slipping off in the event of an earthquake. Purchase chemicals in shatter-resistant, safety-coated containers whenever possible. Actively manage your inventory. Identify and remove for disposal chemicals that become more dangerous with age, contaminated, or exposed to air.
Hazardous waste is any material that is used, spent, unused, unwanted, unusable, or without an obvious purpose. This can include opened and unopened containers, samples, and even contaminated labware or equipment. Your institution is obligated to have a detailed written hazardous waste plan and provide you with training that is specific to your procedures. Follow these best practice guidelines for hazardous waste management. 1. Plan to minimize how much hazardous waste you will generate before you begin your work. Use containers that are compatible with the waste itself, and be sure to choose the right size for your containers, not too small and not too big. Determine what waste can or cannot be added together. 2. Prevent the generation of mixed waste, chemical waste combined with a biological agent or radioactive material. 3. Segregate, do not commingle all waste according to type. 4. Complete all sections of the hazardous waste labels used by your institution. 5. Keep containers sealed and collection areas wiped clean and organized. 6. Evaporation is not an acceptable waste disposal method. 7. Place liquid waste containers into secondary containers to prevent leaks and spills. 8. Prepare your waste containers for removal when no more than 3/4 full. 9. Always deface empty hazardous waste containers, and if necessary, rinse them with the appropriate solution before disposing of them into regular trash or glass waste. Collect rinses in a waste container. 10. Many institutions require a regularly scheduled disposal of biological and chemical hazardous wastes. And finally, 11. Plan and prepare for spills and leaks by keeping spill supplies readily available. Working alone is especially dangerous when those involved have little research experience, such as undergraduates, or those who have not demonstrated competency working with a new hazard. Working alone in a laboratory is strongly discouraged for many reasons. If something serious happens, you may not be able to self-rescue. Your judgment may be impaired. For example, if you have a major spill, or even in a minor emergency. Fatigue may lessen your response. However, there are situations where it may be necessary to run an experiment overnight or unattended. Some examples include chemical reactions, running a centrifuge, drying a sample, performing electrophoresis, or cell culture. Unattended operations require thoughtful planning, communication with your lab mates, and some form of notice in the event of a problem. Many research institutions have special guidelines. Check with your health and safety program for guidelines for working alone and unattended operations. Creating a safe work environment requires intent, conscientious planning, organization, and good housekeeping. Remember these important key action items. Employ a thorough risk assessment in planning and conducting experiments. Insist on good housekeeping. Set aside days to clean up and establish policy for those leaving the lab to clean up as a final step before their last day. Manage, handle, and store your hazardous materials wisely. Plan to minimize hazardous waste. Label containers, store appropriately, and dispose of all hazardous waste in a timely fashion. Avoid, better still, prohibit working alone. Show good judgment when allowing others into the lab. Plan for and discuss how to respond to emergencies with your coworkers and PI. And finally, always follow institutional guidelines.
Laboratory incidents caused by biological, chemical, or radiological hazards often receive more attention than the predictable incidents caused by physical hazards. This is understandable. If adequate precautions are not in place or not followed, the chance of an incident increases with the frequency of the task or use of laboratory equipment. Sometimes, for whatever reason, we may continue to work in the same unsafe way until something happens. Infrequent but high-consequence events often become news events. After an incident, we may realize that what we were doing all along was unsafe, or the equipment we were using was not quite right. Maybe we were tired, maybe we were in a rush, or maybe we felt that asking a question would make us look bad. Recognize these moments for what they are: an opportunity to improve laboratory safety and improve safety culture, and use the opportunity to correct unsafe conditions and practices immediately. Let's begin by addressing physical hazards in the laboratory. When you consider the frequency of all the tasks done in a typical day of lab work, you face a greater risk of an incident caused by a physical hazard in the laboratory than from other potential causes. Physical hazards of one sort or another are found in every lab environment. Some of these hazards you might not have thought of, but they include water on the ground or items on the floor and objects in the walkway, causing slips, trips, and falls. Other, more obvious physical hazards include sharp objects and needles, causing cuts and puncture wounds. Electrical hazards can cause electrical shocks, and open flames, extreme hot or cold objects, or materials can cause burns. Some labs work with systems under pressure, but many incidents are associated with common ergonomic problems like lifting and twisting motions, repetitive manual tasks, or the use or misuse of laboratory equipment or furniture. In this section, we will briefly discuss these physical hazards. You can find additional material in the reference section of this course. Slips, trips, and falls account for a significant percentage of all workplace incidents, including in the laboratory. The potential causes are layout and arrangement of equipment and furniture, clutter, and items on the floor or in walkways. Other potential causes include spills on the floor, standing on stools or chairs, climbing on bench tops, or reaching beyond your limits. Good housekeeping and organization will eliminate most slips, trips, and falls. Clean and organize your work area at the end of each day. Share the responsibility for keeping common areas clean and organized. A proper step stool with self-locking legs is an essential piece of equipment to have in any lab. If you do not have one or cannot share one with another lab, order one right away. During your lab meetings, discuss housekeeping needs and assignments. Schedule periodic cleanup days, especially near the end of the term, to remain organized, efficient, and safe. Recycle obsolete equipment and electronics. Laboratory work may involve prolonged sitting or standing, awkward postures, repetitive tasks, lifting and reaching, or long hours at the computer. Even low-force, high-frequency tasks like pipetting can cause physical discomfort. These forms of postural stress can lead to uncomfortable, painful, and chronic conditions called cumulative trauma disorders or repetitive strain injuries. Ergonomics is the relationship between the human body and the work environment. In the laboratory, a number of prevention strategies, combined with individual awareness and adjustments, can help prevent or alleviate ergonomic stress. A collection of resources on ergonomics is included in the reference section of this course. Modern science depends on electrical equipment, and modern laboratory design provides supply and outlets. The electrical power used to supply common lab equipment is sufficient to cause serious to fatal injuries. As little as 10 milliamps can result in a painful shock. 100 to 200 milliamps are often fatal. Taken for granted or treated carelessly, electricity is an unseen and potentially deadly hazard. Improperly maintained, damaged, or neglected electrical equipment is also a leading cause of laboratory fires. Ensure all laboratory equipment is certified by a nationally recognized testing organization and maintained and used according to the manufacturer's recommendations. Select each item to learn more.
The manufacturer must independently certify that all equipment meets accepted safety standards. Look for a certification stamp or seal. Read and retain the manual that comes with each device. Complete warranty registrations so that in the event of recall, you will be notified. Look for damaged plugs, supply cords and outlets, and have them properly repaired. Never use or continue to use damaged equipment. Isolate electrical equipment from water and flammable liquids. Immediately remove from service any equipment that overheats, trips an outlet, or causes a shock to the touch, no matter how mild. Never touch electrical equipment with wet hands or contaminated gloves. Remove damaged, malfunctioning equipment from service and label "Do Not Use." Once unplugged, use electrical tape to wrap the plug and prevent its use. Remember to turn off and unplug equipment when not in routine use. This also saves energy. With power supplies, handle one lead at a time. Make both connections and then turn on the supply. When needed, develop and post a step-by-step set of instructions on equipment operation and safety.
It's important to remain focused on these everyday electrical safety reminders. Select each image to learn more.
Ensure the outlets around your sinks have GFCI protected outlets. GFCI outlets provide an extra measure of protection, especially around water. Modern design codes require GFCI outlets in renovation projects and new construction. Power strips, extension cords, and high current equipment. Power strips are designed for low-demand equipment that usually draws small amounts of current or operates intermittently like computers. Never connect one power strip to another. Never daisy-chain power strips together. Never use light-duty lamp cord-type extension cords. Connect refrigerators, freezers, and other high-current equipment directly to an outlet. Never use an extension cord or power strip for high-demand equipment. Never overload outlets or use ground-defeating plugs that convert 3 electrical blades into just 2. Disconnect equipment with damaged power cords and place out of service. Contact a licensed electrician for all installations, upgrades, and repairs. Never use extension cords, even heavy gauge, as permanent wiring. Connect refrigerators, freezers, and other high current equipment directly to a wall outlet.
Lab equipment that requires more than just a simple plug and cord connection is directly wired to the building electrical system. Only a qualified service and repair technician should service, modify, or repair laboratory equipment. Never undertake repairs or modifications on your own. Lock out, tag out the equipment when not in use or idle for repair to prevent unauthorized use. Additional information on the concept of lockout, tag out is included in the reference section of this course. In a lab, any object that can cause a cut, laceration, or puncture wound is considered to be a sharp. For example, broken glass, pipettes, razor blades, scalpels, knives, and needles are all considered sharps. Certain lab equipment, such as microtomes and cryostats, use very sharp blades to thin section tissue. Microtomes and cryostats are well known to cause cuts and lacerations. Injuries to the hand account for a significant percentage of all laboratory accidents. Index fingers and thumbs are the most likely to be injured. Cuts, lacerations, and puncture wounds often occur when the dominant hand applies force to an object. Non-dominant hand injuries are associated with a loss of control, such as when something breaks or involves improper hand placement. For example, forcing a glass tube through a rubber stopper. Hand injuries involving sharps can be prevented with patience, forethought, and the use of cut-resistant gloves. While no glove is puncture-proof, modern cut-resistant materials like Kevlar lessen the likelihood or severity of injury when something is inherently sharp, breaks, slips, or snaps. Your safety advisor can help find the right glove for your needs. Also, if you work with syringes and needles, avoid recapping whenever possible. Chipped, Fractured, badly etched, or stressed glassware may break or shatter, causing injury. Meticulous handling and close inspection with a bright or polarized light can reveal potential flaws. Learn from an experienced colleague and employ additional precautions such as cut-resistant gloves. Select each image to learn more.
Recycle and replace damaged glassware. Specialty glassware is typically more expensive, specific to an application, or sometimes custom-made. It is often used in applications involving high or low temperatures, or positive or negative pressure, and may have complex fittings and connections. It is best practice to develop detailed procedures for the safe handling, assembly, disassembly, cleaning, inspection, and storage of specialty glassware.
Some experiments require the use of positive or negative pressure to produce a desired result. Chemical reactors, pressure vessels, calorimeters, combustion vessels, desiccators, and related equipment are all examples of devices and systems that rely on pressure. Pressure is useful in moving reactants from one vessel to another, often in combination with a vacuum. The consequences of system failure may range from minor to serious, depending on the size, pressure, and constituents of the system. The Schlenk line is an example of a system that uses an inert gas and vacuum to manipulate air-sensitive chemicals. High positive pressure may be used to catalyze reactions that would not happen under ambient conditions. Often, the system is heated. Here are some basic safety recommendations for systems under pressure. Risk assessments must be made and should include analysis of all chemicals and physical hazards. Create a written procedure, including what to do in an emergency. Make sure lab personnel are trained on that written procedure. Set up the apparatus inside a certified laboratory fume hood. Place blast shielding around the system. Label the directions of the gas or product flow. Use containers, trays, or other means that can hold at least 10% of the liquid volume in the event of leak or spill. Prominently label and contain systems under pressure when running unattended. Additional safety precautions include the following. Critical systems that might explode or implode must have some method of pressure relief. Use only matching, paired parts. Do not mix and match from a single manufacturer. Use heating units that will automatically shut off in the event of a system failure. Higher pressures equate to greater risks, so enhanced PPE may be required. For example, face shields in addition to chemical splash goggles. Make sure that modifications to commercial reactor pressure vessels do not defeat design safety features. And take extra precautions. If the system must be run unattended, post signs with contact information and the system contents. All compressed and liquefied gases pose physical hazards. Depending on the contents of the cylinder, additional physical and health hazards may exist. Key facts. A failed gas cylinder can accelerate to a lethal velocity in a fraction of a second. Gas regulators are specifically designed for their application and type of gas. It is imperative to ensure you have the proper type or types. Large gas cylinders must be secured to casework or the wall at all times. Store gas cylinders with their safety caps on if they are not in use. Flammable gas cylinders must be stored 20 feet away from oxidizers and oxygen gas cylinders. Never roll, scoot, or transport large cylinders without a specially designed cylinder cart. The safe use of gas cylinders requires additional training and guidance from a qualified person using accepted practices defined by your institution's safety program. High or low temperatures play an important role in many types of laboratory research. Temperature extremes pose an immediate risk of thermal burns. Select each image to learn more.
Extreme cold. Cryogens are substances that exhibit very low temperatures. Liquid nitrogen is a well-known example. Dry ice is a solid carbon dioxide that sublimes to carbon dioxide gas. These substances are considered hazards because of the potential for cryogenic burns, asphyxiation, and catastrophic container failure. Cryogens may also condense oxygen out of the atmosphere, posing a fire or explosion risk. High temperatures. From extreme cold to high temperatures, a wide range of laboratory devices function at high temperatures, posing a burn or fire risk. Read and follow the manufacturer's recommendations and allow plenty of clearance around each device.
Depending on the lab, there can be a simple to complicated array of equipment. For each device, keep the manufacturer's directions and organize this material for easy reference. When helpful, create a standard operating procedure or checklist for easy reference. When purchasing expensive equipment, ensure a manufacturer's maintenance contract is part of the order. At the end of the day, the last person to leave should check to ensure that devices are properly shut down or secure and working properly if they must remain on. The checklist makes this easy to do.
Which statements apply to physical hazards in the laboratory? Select all that apply, then select Submit. Result in fewer incidents than other lab hazards, easy to recognize and control, reduced by good housekeeping and organization, may result in personal injury or physical damage.
Any unwanted sound is considered noise. Noise may be annoying, distracting, or potentially harmful. Ultrasonic noise may be imperceptible, yet damaging. If noise is a potential concern, ask your safety advisor for an evaluation and consultation. Effective noise control addresses the source by removal, adjustment, or attenuation. If this is not possible, or the cause intermittent, appropriate hearing protection is often used. In most situations, hearing protection is effective and easy to use.
That's right.
Physical hazards, including those associated with equipment, are ubiquitous in all but the most basic laboratory environments. As just discussed, identifying and analyzing physical hazards is the first important step in creating a safe laboratory environment. Chemical hazards are also common in many laboratories, and the risk depends on several factors, including their intended role in the research. For chemists, the role of chemicals in their lab is self-evident. For life scientists, engineers, and others, the role of chemicals in their research projects may be a necessary ingredient in an experiment. Chemical safety depends on understanding the chemicals used and stored in your laboratory, as well as their hazards and risks. Never underestimate the potential harm that mishandled chemicals can cause to individuals, public health, or the environment. Chemical safety is a necessity in nearly every laboratory and is discussed here in detail. Identifying chemical hazards and assessing their risk is an essential laboratory skill. If the chemical or chemicals in the experiment are well known and documented in a published procedure, then the risk assessment relies on prior knowledge and experience. If the chemicals are to be used in a novel way, or if the published procedure is altered, the risk assessment must be more rigorous. Dig deeper in the literature, consult with your PI and known experts. Either way, start with a thorough review of the literature in planning your experiments. Safe science is good science. Safe science is based on a thorough understanding of what is known and identifying what may not be known. Select each step to learn more about chemical risk assessment.
First, read the container label and identify the primary hazard. Then, read the most recent safety data sheet available in order to identify what hazard information is known and, just as importantly, determine what is unknown. Look for any special hazards and include them in your lab notes and share with others. Follow the standard operating procedure for the chemical if it is hazardous. In the SOP, identify and plan for potential emergencies. Identify the appropriate PPE to wear in advance and keep an extra set available in case of spill. PPE should also be specified in the SOP. If possible, minimize the amount of chemicals and waste in your experiments. Set up and label your waste containers before starting work. Prepare to work inside a well-organized, certified laboratory fume hood. For highly hazardous procedures, it is advisable to do a test run without the hazard before conducting the real experiment.
Around the world, chemicals are classified for transportation and handling based on their immediate or primary hazard that could be corrosive, flammable, and/or combustible, reactive, such as an oxidizer, and toxic, such as poison. The primary hazard is largely based on the immediate properties of the chemical and is also a reliable indicator for purposes of classification, handling, storage, and disposal in the laboratory. Chemical hazards can be identified as physical hazards, for example, flammability or reactivity, and health hazards, for example, carcinogenicity or sensitization. Many chemicals have more than one physical hazard, and often have potential health effects as well. For simplicity, we describe these as secondary hazards. There may be several secondary hazards, and all of them may pose a risk. The most immediate source of primary and secondary hazard information is on the manufacturer's chemical container label. By law, chemical labels must be standardized. According to the Occupational Safety and Health Administration, the Hazard Communication Standard, HCS or HAZCOM, requires chemical manufacturers, distributors, or importers to provide safety data sheets, SDSs, to communicate the hazards and risks associated with a particular chemical. SDSs for most chemicals are easily accessible online. Ensure that any SDS you consult matches the particular chemical in question. Click each highlighted section to learn more.
Section 1. Identification includes product identifier, manufacturer-distributor name, address, phone number, emergency phone number, recommended use, and restrictions on use. Section 2. Hazard identification assigns the hazard classification and includes routes of entry into the body, required label elements, work precautions and PPE recommendations, and important information about storage, waste management, and spill response. Section 3. Composition and information on ingredients includes information on chemical composition, CAS number, and trade secret claims. Section 4. First aid measures include symptoms and important acute and delayed effects, required treatment. Section 5. Firefighting measures list suitable extinguishing techniques and equipment, special hazards that can arise from the fire. Section 6. Accidental release measures lists emergency procedures, protective equipment, proper methods of containment and cleanup. Section 7. Handling and storage lists precautions for safe handling and storage, including incompatibilities. Section 8. Exposure controls and personal protection lists OSHA's permissible exposure limits, ACGIH threshold limit values, and any other exposure limit used or recommended by the chemical manufacturer, importer, or employer preparing the SDS, as well as appropriate engineering controls, personal protective equipment. Physical and chemical properties list the chemical's characteristics. Stability and reactivity lists chemical stability, possibility of hazardous reactions, and incompatibilities with other chemicals. Section 11. Toxicological information includes routes of exposure, related symptoms, acute and chronic effects, numerical measures of toxicity. Section 12. Ecological information. Section 13. Disposal considerations. Section 14. Transport information. Section 15. Regulatory information. Note, Sections 12 through 15 are more important to other agencies. Section 16. Other information includes the date of preparation or last revision.
Flammable and combustible chemicals represent a broad range of simple to complex molecules that can ignite and burn. These chemicals are often liquids, but also include gases and solids. Flammable gases and solids have their own special hazards and risks, the details of which you can learn beyond this course. Special engineering controls are required for flammable gases. Flammable solids, particularly metals, require specialized fire extinguishers and emergency procedures. Check with your safety program to understand the limits placed on the type and volume of flammable chemical you may store in your lab. Institutional requirements vary, so always check first. Here are some general practical guidelines. Store no more than 20 gallons of any flammable liquid in a single contiguous lab space inside certified, self-closing flammable storage cabinets. Store no more than 4 to 6 gallons in the flammables cabinet beneath a laboratory fume hood. Self-closing certified flammable storage cabinets do not prevent fires per se, but they provide an extra margin of safety. In the event of a lab fire, a latched flammables cabinet protects the contents inside from accelerating the fire. Never underestimate the hazard and constant risk of storing flammable liquids. They remain a hazard 24 hours a day and 7 days a week. Limit your inventory to the smallest practical volume to meet your needs. Never purchase more than you will use in 6 months. Flashpoint is the lowest temperature at which a flammable liquid gives off enough vapor to form an ignitable mixture in air when a source of ignition is present. Flashpoint is used to classify flammable liquids. The lower the flashpoint, the greater the hazard. A simple rule to remember is that a flashpoint at or below room temperature is a real concern because the chemical can easily ignite and burn. Minimize the amount of flammable liquids on the bench and control sources of ignition. It is best to wear a flame-resistant lab coat. Handle large amounts inside a laboratory fume hood. Refer to safety data sheets for more information about a chemical's flashpoint and flammable range. Vapor pressure is a useful measure of how easily a chemical can enter the atmosphere. It is a measurement of the pressure exerted by a vapor over its liquid in a closed container. Liquids with low flash points like ethyl ether and acetone have high vapor pressures. Ethyl ether and acetone have flash points below room temperature. Do not store Category 1 and 2 flammable liquids inside a conventional refrigerator or freezer. In a conventional refrigerator or freezer, the compressor or interior lights act as a potential ignition source. Refrigerators and freezers rated for flammable storage are specially designed and certified. Oxidizing materials cause decomposition or accelerate combustion. Chlorine is an example of a powerful oxidizer. Store or segregate oxidizers from combustible or flammable materials and liquids. Do not store oxidizers together with organic solvents and reducing chemicals. Common oxidizers found in the lab include nitric acid, nitrates, perchlorate salts, and hydrogen peroxide. Pyrophoric chemicals are a classification of solids, liquids, and gases that spontaneously ignite upon contact with air. These chemicals are extraordinarily dangerous. Make sure to receive special training and follow all precautions, including using a flame-resistant lab coat and, if required, flame-resistant gloves. Unlike the formal conventions used to create the primary hazard classifications used in shipping and commerce, the broadly applied term reactives refers to chemicals that, if not properly handled, may release large amounts of energy. Sodium is an excellent and well-known example of a reactive chemical. In this picture, we see sodium reacting with water. Shown here are examples of chemicals that react violently with water. The term reactives also refers to chemicals that become unstable over time. For example, some chemicals form unstable peroxides when exposed to air. Other examples include chemicals that become dangerous when allowed to dry out, chemicals that react in the presence of moisture in the air or when wet. These types of chemicals require special storage conditions described in their SDS. It is important to date time-sensitive chemicals when they arrive and dispose of them before they expire. Corrosives are solids, liquids, and gases capable of damaging materials and living tissue. With a neutral pH being 7, corrosives are formally classified at the opposite ends of the pH scale. Greater than 12.5 is a strong base. Less than 2 is a strong acid. But even mild acids or bases, especially when concentrated, can be corrosive to sensitive organs such as the eye. The following are tips for working with and storing corrosives in the lab. Segregate corrosive chemicals by type, acids away from bases, and store inside plastic bins as secondary container to protect against spills. When collecting corrosive wastes, select compatible containers. Never mix incompatible chemicals. Whenever possible, purchase corrosives in shatter-resistant containers and store in a cabinet designed for corrosives. Add an acid or a base to water slowly to minimize the exothermic reaction that takes place. The easy-to-remember AAA, or always add acid, is good advice to remember. Any chemical or substance in sufficient quantity can be toxic. Conceptually, this makes sense. But practically, it is meaningless when assessing the risk associated with toxic chemicals in a laboratory. In this section, we will distinguish between acute and chronic toxicity. Acute toxicity is when a single exposure causes an adverse effect or outcome. Acutely toxic chemicals are often associated with the widely recognized skull and crossbones, denoting a poison. Chronic toxicity is when repeated or long-term exposure or exposures cause an adverse effect or outcome. Mercury, lead, and formaldehyde are examples of chronic toxins. Segregate toxics from other hazard classes and store them in a cool, well-ventilated area away from light and heat. This simple model is useful in evaluating potential toxicity. It involves assessing 4 basic variables: duration of exposure, dose or amount, route or routes of entry, and frequency of exposure. Other factors that influence toxicity include the differences between individuals, environmental factors, and predisposition to exposure. The accepted measure of acute toxicity, LD50, is the amount of a toxic material, often in food or drink, that causes the death of 50%, one-half, of a group of test animals, typically lab rats or mice. A related measure for inhaled chemicals is the LC50 value. The LC50 measures the lethal airborne concentration. Professor Karen Wetterhahn died of a single acute exposure to dimethylmercury, an organometallic compound considered super toxic. Please remember 2 things from this tragedy. Some chemicals are toxic in tiny amounts, and the warning information for skin contact may be limited or non-existent. For very toxic compounds, take extraordinary precautions to avoid contact by any. Particularly hazardous chemicals are sometimes described in more detail using the terms below. Select each item to learn more.
Carcinogens, chemicals that are known or reasonably suspected to cause cancer in animals or humans. Mutagens, chemicals that are known or reasonably expected to cause genetic damage. Reproductive toxins and teratogens, chemicals that interfere with sexual function and fertility and may cause birth defects. Specific organ toxins, chemicals that are known or reasonably suspected to damage specific organs in the body, blood, liver, kidneys, lungs, etc. Chemicals with low warning properties. Chemicals such as carbon monoxide and nitrogen dioxide are known to cause harm but lack any obvious odor, appearance, sensation, or other warning property. For some chemicals, the warning properties are only perceptible at concentrations considered harmful or deadly. Irreversible effects. Exposure may cause immediate harm or death. An effective first aid method or antidote may not exist. Highly toxic gases like diborane, fluorine, and nitrogen dioxide are difficult to contain or control with standard lab engineering. Reach out to your institution's safety program for advice and guidance before working with these toxic gases.
Let's review hazard identification and risk assessment with laboratory chemicals. 1. Identify the immediate or primary hazard of the chemical or chemicals. 2. Make sure to be trained and competent when working with the hazardous chemical. 3. Read the most recent safety data sheet. 4. Determine the routes of entry into the body. 5. Evaluate the degree of toxicity, acute versus chronic, particularly hazardous, etc. 6. Know the signs and symptoms of exposure. 7. Select and use the proper means of control, typically a recently certified laboratory fume hood. 8. Wear properly selected personal protective equipment. 9. Report known or suspected exposures. 10. Be prepared to respond to emergencies. 11. Do not work alone in the lab when working with highly hazardous chemicals.
Which of the following statements apply to a chemical risk assessment? Select all that apply, then select Submit. Ensures your experiment is safe. Assists in the selection of appropriate work environment and personal protective equipment. Provides the basis of a written procedure to follow. Identifies known and unknown hazards and risks. Begins with a review of the scientific literature.
In this section, we discuss the importance of good housekeeping and the role it plays in creating a foundation for laboratory safety. Physical hazards represent a set of hazards and risks that are sometimes taken for granted. The identification and control of chemical, biological, and radiological hazards is based on a risk assessment. A well-done risk assessment plays an important role in developing effective written procedures. Following established written procedures helps ensure safe, consistent outcomes in laboratory research. In the next module, we will turn our attention to controlling the risks identified in the laboratory.
Early in this program, we introduced the concepts that form a laboratory risk assessment. In this section, we will introduce another useful concept of a continuous lab safety improvement approach to control potential exposure and minimize risk. Continuous lab safety improvement includes the following steps. 1. Check the most recent literature in your field for safer alternatives and procedures. 2. Eliminating potential hazards entirely if possible. After all, you do not have to manage hazards that do not exist. 3. Substituting less hazardous chemicals or processes whenever possible. 4. Using the smallest practical amount of all hazardous materials in your research. 5. When modifying or changing the experiment, such as scaling it up, changing the catalysts or order of addition, analyzing and discussing the risks and consequences before making changes. 6. Safely containing the hazardous material and processes, typically inside a laboratory fume hood. 7. Taking advantage of temperature controls, automatic shutoffs, and additional shielding whenever they add an extra measure of protection. 8. Wearing properly selected personal protective equipment at all times. 9. Planning and preparing for potential emergencies. 10. Communicating with your colleagues, coworkers about your work. Posting updated signs and notices on your workstation to inform others of safety-sensitive work. The continuous lab safety improvement approach complements what is called the traditional hierarchy of controls in health and safety. In the following, we will focus on engineering controls, administrative controls, and personal protective equipment. You will learn more about how all these pieces fit together to form a reliable framework in laboratory safety next. As teaching and research science has become more sophisticated, so have the laboratory facilities that house and support the work of scientists. Since hazardous materials and equipment play an important role in laboratory science, safety must always be a key consideration in the design, renovation, and maintenance of science facilities. Engineering controls like laboratory ventilation, laboratory fume hoods, biosafety cabinets, and chemical storage cabinets are dedicated features that provide enhanced health and safety protection. Understanding the important role of these features is essential. Ventilation is an important engineering control. Select the icons to learn more.
General building ventilation. General laboratory ventilation provides occupant comfort, heating, and cooling. General lab ventilation is not intended to control volatile chemicals used on an open bench. Therefore, only use volatile chemicals in a laboratory fume hood or exhausted enclosure or with a dedicated spot ventilation. Laboratory fume hoods. Laboratory fume hoods, sometimes also called chemical fume hoods, provide local exhaust ventilation and serve two important functions. The first is convenient and isolated space to work with any type of hazardous chemicals, and the second is the controlled movement of air that isolates you from toxic fumes, vapors, or dust. The movement of air also dilutes the contaminants as they are exhausted out of the building. When used properly, the laboratory fume hood also provides protection against exposure to splashes, sprays, and the sudden release of hazardous chemicals. It can contain an accidental small fire as well. Please refer to the reference section to learn more about some of the specialized ventilation systems, such as lab hoods, cabinets, glove boxes, and other devices for specific needs.
Fume hoods are one of the most important safety features in a research laboratory. The hood is used to protect researchers from breathing hazardous airborne chemicals, and the sash can be used for protective shielding. This presentation demonstrates how to use your fume hood properly to better protect yourself and our environment from exposure to hazardous materials. When you use the hood, you should turn on the hood light so you can see clearly. Check the hood certification sticker. It will list the date Facilities Management last checked the hood, the average inflow, and whether the airflow was satisfactory. One should always check the quantitative airflow monitor or alarm to verify that airflow for the fume hood is proper. There are several types of airflow monitors used on campus fume hoods. For this video, we will show you a few of those common types. Digital monitors display air velocity into the hood and should read more than 100 feet per minute. Some monitors will only display red, yellow, and green indicator lights. All monitors have an audible low flow alarm. Some fume hoods have differential pressure monitors that look like this. Since these monitors may be different from building to building, check with your supervisor for the correct meter reading. It should always be greater than 0. If the hood airflow monitor indicates low airflow, first try lowering your sash. If this does not resolve the alarm, contact your Department Safety Coordinator, EH&S, or Facilities Management for maintenance. Adjust the sash to the proper height. In this case, the glass sash was raised to the maximum working height as indicated by the joined arrow, and then slightly lowered. The tissue on the sash is drawn in, indicating that there is airflow into the hood. Most fume hoods now have this label on the sash frame. Be sure to use the sash in the green zone as much as possible. A sash should only be in the red zone for equipment setup. When you are finished with your work, be sure to lower the sash and save energy and protect lab occupants. Airflow turbulence at the front edge of the hood can draw airborne contaminants out of the hood. In this case, the sash is too high, and when someone walks by, the low inflow velocity allows the smoke to come out of the fume hood. Sashes properly adjusted and working further into the hood are the best way to protect yourself from inhaling hazardous chemicals used in the hood. Move extra equipment out of your way and always work at least 6 inches from the front of the hood. Some hoods have a combination sash that can be opened horizontally or vertically. In this case, the sash is lowered, then the horizontal sash is adjusted to provide protection from explosive reactions or chemical splashes. In older buildings, fume hoods may have horizontal sliding sashes and a velocity screen to meet the 100 feet per minute inward face velocity. Horizontal sashes need to be placed in front of the work and the velocity screen lowered to maintain a safe working environment. Typically, there are no pollution control devices on fume hoods. The airborne contaminants made in a laboratory hood are exhausted from the roof stack into the environment. Never evaporate chemical waste through a hood, and when working with a hood, minimize the volatiles released to protect our air quality. When you are done using volatile chemicals, close and seal the container. When finished using the hood, close the sash and turn off the light for added safety and to save energy. In review, before using the hood, check the airflow monitor. Properly adjust the sash height for your work. Always work at least 6 inches from the front of the hood. Fume hoods exhaust into the environment. Minimize your fume hood emissions. Close the sash when you are done working in the hood. In closing, if you have questions about your fume hood, ask your lab manager, department safety coordinator, or contact the Office of Environmental Health and Safety. Also, Read the fume hood safety net and other laboratory safety information available at the EH&S website.
Biosafety cabinet. Properly maintained biosafety cabinets must be used whenever procedures with a potential for creating infectious aerosols or splashes are conducted and when high concentrations or large volumes of infectious agents are used. Watch this video to understand the function and proper operation of a BSC to prevent exposure. Biological safety cabinets versus laboratory fume hoods. Biosafety cabinets and laboratory fume hoods are not the same. Fume hoods have no filtration of air, exhaust chemical fumes outside the laboratory, suitable for chemicals and non-sterile work, must be certified annually. Biosafety cabinets, Class 2 Type A, HEPA filtration system of air to intake and exhaust, recirculates HEPA-filtered air into laboratory, utilized to ensure sterility and containment of infectious agents, must be certified annually. Snorkel hood. There are other specialized local exhaust ventilation systems in laboratories. One such device is the snorkel or trunk hood. These flexible, ceiling-mounted devices allow ventilation to be placed where it is needed. With less protective than a laboratory fume hood, they can capture volatile, hazardous chemicals at the source while working with well-controlled activities on the bench. These must be certified annually. Follow your institutional policy on their application. Discuss with your safety program before use. Sound of silence. By design, science buildings must move a great deal of air for both general and local exhaust needs. If the building falls silent because the ventilation system has shut down, stop work immediately. Close your containers and lower the fume hoods. Do not resume work until the ventilation system is running again properly. In order to keep the ventilation system running, maintenance staff must shut it down periodically, change filters, and replace belts and motors. Your facility staff will provide plenty of notice during planned shutdowns. Please take the time to read and follow their notices, and please do not resume your work until the building is restored to service. In the event of system failure or emergency repair, please be understanding and patient. You must not work with any type of volatile or airborne hazardous materials until you are told the system is up and running safely again. Which of the following statements are important concepts in laboratory ventilation? Select all that apply, then select Submit.
For practical reasons and as required by law, research institutions are required to have written policies and procedures on laboratory safety. This includes safety training. These documents are known as administrative controls. There is a myriad of labor regulations to protect workers and environmental regulations to protect the air, land, and water. Your institution is obligated to follow these requirements, and in turn, this obligates you to follow the policies and procedures of your host institution. Federally funded grants and corporate-sponsored projects are awarded to research institutions with explicit terms and conditions, including worker safety and environmental protection. The reputation of the recipient and the institution is leveraged in these commitments. To fulfill these obligations, each laboratory must have a current research registration on file with their institution. Research registration processes vary by institution. In all cases, a research registration must include a description of the research projects, the individuals involved, and where the work is taking place. Your research registration will fit within the matrix of labor and environmental regulation that your institution must follow. Keeping it up to date is the easiest way to ensure you are in good standing. So remember, add and remove personnel as they come and go. Ensure your project summaries are clear and succinct. Make sure everyone's training is up to date, and keep your registration current. The Occupational Safety and Health Administration, OSHA, and its Laboratory Safety Standard require each teaching and research institution to have a formal, written Chemical Hygiene Plan, CHP. This Chemical Hygiene Plan is an essential administrative control. The CHP should be up to date, address a number of prescribed elements, and be readily available to lab personnel. Key elements of the CHP include managing chemical storage and inventory, ensuring proper waste management, requirements for record keeping, signs and other forms of warning, standard operating procedures, and availability of safety information, including safety data sheets, spill response and emergencies, training requirements, periodic inspections, availability of medical consultation services. Please review the chemical hygiene plan of your institution. To inform and protect those who enter your lab, especially those involved in maintenance or emergency response, appropriate safety signs are required by law. The doorway into the lab represents the point where the research registration of the work inside is translated into practical terms as defined by the administrative policies of your institution. It is important that the information found on each entryway be kept current. In the event of an emergency, this may be the only reliable source of information on who to contact. Please do not cover the windows that allow a view into your lab from a hallway. In the event of an emergency, this may be the only safe way to determine if anyone is inside. Do not remove or deface the label provided by the manufacturer on any original container unless you dispose of the empty container. For stock solutions and other working mixtures, you may create your own label with the name of the chemical, the date made, the name of the person who made it, and any special warnings, such as flammable, corrosive, toxic, and so on. Standard operating procedures, SOPs, or guidelines are often developed for quality assurance and safety. Like a kitchen recipe, an SOP is an outline to follow. Well-written SOPs help ensure safe, predictable outcomes. In high-risk activities, SOPs help prevent potentially harmful mistakes caused by such things as the incorrect order of addition in reactions, using too much or too little of key ingredients. SOPs also point to the proper protective equipment. Not every task requires an SOP, but every safety-sensitive, high-consequence experiment deserves a well-thought-out plan that is written down. Begin with a well-done risk assessment. Safety Training Consortium members work to share existing SOPs or their templates. For existing lab procedures and protocols, simply add in key safety reminders as part of the document. Please remember, SOPs do not need to be complicated to be effective. Some institutions require an SOP for every hazardous chemical in your lab. Follow the guidance of your institution's safety program. There are some experiments that pose novel or special risks. Examples include experiments where the hazards of the work may overwhelm the standard engineering controls or personal protective equipment, or pose a risk to others in the building or the environment. Seek help from your safety program to obtain prior approval when planning any high-risk experiments. It is always time well spent. Authorizations are required for work involving biological agents, radioisotopes, animal use, laser hazards, X-ray producing machines, controlled substances, and toxic gases. Experts can often be found in your institution, often on your safety committees. Colleagues, peers, and experts at other institutions are also valuable resources in planning high-risk, high-consequence experiments. An effective safety program and a healthy safety culture include periodic laboratory safety reviews. This typically is a combination of inspections, audits, and updates to your research registration profile. Please discuss laboratory safety during each lab meeting. Putting it on the agenda makes it a priority.
Assume you are working with an acutely toxic chemical. Select all administrative controls relevant for your project: chemical hygiene plan, biological use authorization, lab-specific training for working with acutely toxic material, standard operating procedure. The Chemical Hygiene Plan provides guidance on which of the following:
Approximately 2,000 work-related eye injuries occur in the American workplace every day. 10 to 20% of these injuries involve temporary or permanent vision loss. Vision experts believe that 90% of all eye injuries can be lessened or prevented with proper eye protection. Years of experience demonstrate that the most effective safety programs require eye protection 100% of the time. Eye injuries in the laboratory may result from flying objects penetrating, blunt trauma, and chemical injuries from spray and splash. UV and other spectra can also cause serious injury. It may seem obvious, but eye protection only works if it is worn. Conventional prescription eyewear is not approved eye protection. Prescription safety glasses match impact-resistant lenses with an impact-resistant frame. The frame must wrap around the orbit of the eye or have side shields on each side to help prevent indirect exposure. Each component of prescription safety glasses, the frame, lenses, and side shields, must be certified and clearly marked. Anything less is not approved safety eyewear. Personal protective equipment, or simply PPE, may be among the first items you put on in the lab to protect yourself, but it also represents the last line of defense. Laboratory coats, eye and face protection, and gloves, combined with proper dress, are all part of an appropriate safety ensemble. It may seem a little surprising, but your first lab safety decisions of the day take place well before you reach your research building. What you decide to wear will either enhance or compromise your personal safety. Appropriate attire for the lab includes covering your legs with pants or slacks. Shorts, skirts, dresses, and other such garments leave skin unprotected even with a lab coat. 100% cotton garments are inherently flame-resistant. Most synthetics are inherently flammable and will melt to the skin if ignited. Wearing closed, substantial footwear with socks, sandals, flip-flops, and flats are not appropriate. As a best practice, keep a dedicated set of sturdy shoes for the lab in your office or locker. If you have long hair, tie it back or otherwise restrain it. Likewise, do not wear loose or dangling jewelry. The reference section provides guidelines for selecting PPE. Polycarbonate safety glasses provide the most convenient and flexible form of eye protection, and they provide impact resistance and limited splash protection, and polycarbonate plastic is inherently UV resistant. Polycarbonate safety glasses can be additionally treated for greater UV protection. Wearing your safety glasses at all times while in the laboratory is a best practice. Because comfort and fit is an important factor in everyday use, safety glasses come in a wide variety of styles and sizes. There are narrow frames for smaller faces, safety glasses with adjustable nose bridges, and even glasses with reading lenses. A practical, low-cost solution to prescription safety glasses is an over-the-glasses design. Over-the-glasses designs allow protection without removing conventional prescription eyewear. Chemical splash goggles provide a higher level of protection against eye injuries by combining the impact resistance of safety glasses with a flexible, complete seal around the eyes. Chemical splash goggles today have curved, spherical lenses. This provides an improved field of view with less eye strain. They are also indirectly vented for comfort. Strong corrosives, even in very small amounts, can cause serious eye injuries, including the permanent loss of sight. Caustic chemicals are known to cause immediate, deep, painful, and potentially widespread damage. Acids, while slightly less damaging than caustics, except hydrofluoric, will coagulate proteins on the surface of the eye. These injuries are also immediate and painful. Chemical splash goggles provide the greatest protection. For work involving 1 liter or more of any strong corrosives, supplement your use of chemical splash goggles with the addition of a full face shield. When selecting eye protection, look for specific certifications to ensure the proper type. Look for an internationally recognized certification, such as Z87, USA, Z94, Canada, CEN TC85, EU. Polycarbonate safety glasses can be additionally treated for scratch and fog resistance. These same criteria apply to prescription safety eyewear. Safety glasses or splash goggles alone do not protect the face and neck. A face shield alone does not provide adequate eye protection. When worn together, a certified face shield with chemical splash goggles provides both eye and face protection. This is the ideal combination for higher-risk energetic experiments. Features to protect the neck are found on many face shield designs. A widely held misconception is that contact lenses cannot be worn in a laboratory. Contact lenses are acceptable in the laboratory, provided that eye protection is worn at all times while in the lab. For systems under high or low pressure, inherently reactive or energetic experiments, or extremes in temperature, place heavy-duty polycarbonate blast shields around critical equipment or systems. In addition to the use of blast shielding, wear chemical splash goggles and a face shield to provide the greatest measure of protection in high-hazard, high-risk experiments. After protecting your eyes, the next step is wearing the right lab coat. In low-risk labs, people often ask, why a lab coat? At a minimum, a lab coat provides an additional layer of protection and helps protect your clothing from contamination. In biotechnology environments, cell culture and basic microbiology inevitably generate droplets and aerosols. While largely invisible, most of us would rather not have these materials follow us home or have them come in contact with our food, friends, family, pets, or vehicles. In other sciences, salts, buffers, finely divided materials, and lubricants can be just as unappealing. The right lab coat for you depends on your work. You can follow these basic guidelines. For work with flammable chemicals, a flame-resistant lab coat, FR-rated or made of flame-resistant specialty fabrics like Nomex, provides a greater measure of protection. Keep your lab coat fully buttoned or snapped at all times. A fully closed lab coat creates a more protective envelope around your body. Remove your lab coat as you leave the laboratory. Never wear a lab coat in common spaces, like a kitchen area, classroom, or library. Make use of your institution's lab coat washing program. Never take your lab coat home to wash. Wearing your lab coat is a visible, conscious reminder that laboratory safety is an individual, institutional, and shared value. In the laboratory, the hands are at constant risk of cuts, burns, punctures, and contact with some combination of biological, chemical, or radiological exposure or physical trauma. Contact with or trauma to the skin is a primary route of entry of hazardous materials into the body. Single-use disposable gloves provide barrier protection against biological, chemical, and radiological materials. They also help prevent your skin from causing contamination of labware and experiments. Latex is a naturally occurring elastomer that is known to cause sensitization and allergies in laboratory workers. Use non-latex alternatives such as neoprene, nitrile, and vinyl. Information on latex allergies is included in the reference section of this course. No single glove can protect you from every hazard. Gloves have limitations. Some chemicals can permeate gloves. Choose the right glove type for your experiment. Watch this video about glove permeation, penetration, and degradation, and look for ways that these elements may affect your choice of glove type. This animation on glove permeation, penetration, and degradation was produced by the Northwestern University Office for Research Safety. The following key terms will be discussed in detail: penetration, permeation, risk assessment, and degradation. Penetration describes how chemicals can pass through a glove material via macroscopic breaks, such as tiny holes, cracks, and tears. Mechanical damage, such as stretching, cuts, or punctures, cause macroscopic breaks. Gloves that are old or poorly made are more likely to fail due to penetration. This illustrates how molecules of benzene can penetrate through macroscopic breaks in a neoprene glove. Permeation describes how chemicals can pass through a glove material on the molecular level. Often this happens without any visible change, sensation, like wetness, or other indication of chemical exposure. This illustrates how molecules of benzene can permeate a neoprene glove. Chemical permeation can be described in simple terms by comparing what happens to the helium in a balloon after a couple of hours. Even in a tightly sealed balloon, the helium inside will permeate through the wall to the atmosphere. This example uses gas permeation, but the principle is similar with liquids and chemicals. Hazardous chemicals may permeate through the glove, exposing the skin to the chemicals. Selecting the proper glove for the chemicals you work with in the lab requires a risk assessment. A proper risk assessment considers all of the following: the chemicals, their concentration, the potential for direct contact, for example by total immersion or splashes, the frequency and duration of contact, and the length to be protected, which can include the hand, the forearm, or the entire arm. Based on their composition and the manufacturer's permeation data, disposable gloves provide only limited chemical protection. Change disposable gloves frequently and whenever there is known or suspected contact. Take these gloves. Let's get back to work. Another important glove concept is degradation. Degradation is a measure of how tough the glove material is when exposed to chemicals. If a hazardous chemical has a significant impact on the physical properties of the glove, then its ability to protect you is compromised, and you risk chemical exposure to your skin. With reusable gloves, replace them when they become discolored, swell, crack, or simply become funky. Wearing improper gloves puts you at a risk of chemical exposure. Always select gloves based on a careful risk assessment and published information by the manufacturer. Consider the potential for penetration, permeation, or degradation. Sometimes the best glove is actually a combination of gloves. For example, a specialty plastic laminate glove worn as a permeation-resistant liner under a heavy-duty outer glove. In summary, choose the right glove for your needs by considering penetration, permeation, risk assessment, and degradation. Single-use disposable gloves play an important role in the laboratory. Purchase quality gloves from a reputable manufacturer, and always check gloves for holes and tears before you use them. This video demonstrates 2 techniques for removing gloves without contaminating yourself. It takes some practice to get the hang of it. The goal is simple: to never touch the outside of the used glove with unprotected skin. Contaminated gloves should be discarded in the container that is designated for the hazard. Uncontaminated gloves may be disposed of as non-hazardous trash. Please do not attempt to reuse disposable gloves. Change your gloves whenever they become contaminated and between experiments. Please do not touch common surfaces such as doorknobs with gloved hands. Also, don't wear gloves outside the lab. Always wash your hands after removing disposable gloves.
Who doesn't know how to remove gloves, right? But can you do it without touching the outside of the gloves? Gloves are a physical barrier between you and the substances you're working with. But what good are they if you contaminate yourself while removing them? Try one of these methods to remove those dirty gloves. The fold and tuck. Grab one glove on the palm side and fold over your fingers. Carefully pull the glove off and ball it up with your still gloved hand. Tuck a finger under the other glove and slowly peel your hand away. Or try the double fold. Start the same way as the fold and tuck. But this time, keep the first glove around your fingers and use it to grab and fold the second glove and pull. All right, you got the gloves off, but now what? Throw them away appropriately. Don't even think about reusing disposable gloves. And wash your hands thoroughly, between your fingers, under your nails, and all that good stuff. Now, let's rewind. The gloves did their job. Now do yours. Remove those gloves slowly and carefully to keep that physical barrier working for you. For that healthy, safe feeling. EH&S, protecting your health and safety.
Heavy-duty reusable gloves come in a variety of materials, thicknesses, and lengths. When properly matched to the task, reusable gloves provide additional protection. When used in combination with disposable gloves and, when necessary, together with other materials, the combined properties can address multiple hazards. The most chemically resistant glove material is made of a laminate plastic and is known by its commercial name, Silver Shield. Silver Shield gloves are most effective when worn underneath a heavy-duty glove. Modern fibers such as Kevlar, Nomex, and Dyneema, combined with improved manufacturing and testing methods, have led to a new array of cut-resistant gloves with practical applications in research laboratories. For some of these new gloves, in addition to cut-resistant, they are also flame-resistant. While no glove is proven puncture-proof, cut-resistant gloves worn over disposable gloves provide enhanced hand protection against cuts and lacerations in the laboratory. Long-cuffed Nomex gloves worn by military pilots for many years are well suited for work with highly flammable chemicals such as pyrophorics, ethers, hexane, and other low flashpoint solvents. Please take proper care of your reusable gloves. Rinse the outside of each glove thoroughly under running water before removing them. Allow the gloves to air dry completely and replace the gloves when they become discolored, tacky, cracked, or old. Specialty grips made of heat-resistant silicone are a convenient form of protection when handling hot liquids and glassware. By design, a laboratory fume hood provides dedicated local exhaust ventilation for work with hazardous materials. A respirator is necessary if engineering controls are not sufficient to protect you from the hazard. A respirator is a type of PPE that is worn over the nose and mouth and is intended to filter out airborne contaminants. Respirators come in a wide variety of types. Each type is designed for a specific application. Assuming a recently certified laboratory fume hood is used and the work does not overwhelm the envelope it provides, a respirator should never be needed. Please do not take it upon yourself to obtain a respirator. In all cases, speak to your safety advisor before considering purchasing or using a respirator. A surgical-type mask is sometimes worn to protect your nose and mouth, especially with blood and body fluids. The two functions of surgical masks are to protect against splash and spray and to lessen the likelihood that expelled droplets become contaminants. For these reasons, they may be useful in a biomedical laboratory. They provide little to no protection against finely divided chemicals and aerosolized biohazards, and do not at all protect against chemical vapors, gases, or nanoparticles.
A graduate student is planning to conduct an experiment with several hazardous, highly flammable chemicals. As he enters the lab, his professor stops him and gives a disappointed look. She tells him he cannot work in the lab until he is properly dressed and is wearing appropriate PPE. At minimum, what should this include? Select all that apply, then select Submit. Long pants made of 100% cotton, flame-resistant lab coat, flame-resistant gloves, chemical splash goggles and face shield, sturdy closed-toed shoes.
This module moved from hazard identification into risk control, emphasizing a number of safe working strategies you can follow to protect yourself and your colleagues from exposure and harm in the laboratory. We also emphasize the importance of making informed and conscious decisions involving the proper use of engineering controls, following established policies and procedures. This process begins each day as you prepare to head to the lab. The proper and consistent use of personal protective equipment, PPE, provides the last line of defense in protecting you against exposure and harm from your use of hazardous materials. In the next module, we turn our attention to emergency planning and response. In this module, we will discuss laboratory security, emergency planning, and emergency response. Security helps protect individuals, property, and safety-sensitive items. Emergencies will always occur. The question is not if, but rather when they will happen. To lessen the impact of these emergencies and to improve your ability to recover more quickly, be sure to plan, prepare, protect, and practice. Laboratory security is an important element in laboratory safety today. Taking reasonable, thoughtful, and practical steps to limit access to your lab, locking up safety-sensitive hazardous materials, and being mindful of potentially dangerous behaviors are all part of improving laboratory safety. When done thoughtfully, this is hardly noticeable. In this section, we will discuss 3 important aspects of laboratory security: physical, computer, and situational security. Together, this forms an effective strategy that supports laboratory health and safety. For a number of reasons, most of all peace of mind, laboratories need to be secured against unauthorized access. Controlling access improves personal safety and lessens the likelihood of theft or the diversion of hazardous materials. Security is a combination of physical barriers, procedural steps, and human behaviors that help prevent, lessen, deter, or delay criminal behavior. Many scientists report that they feel more comfortable and relaxed in facilities that have limited access. Restricted access means that unauthorized persons cannot wander into a research building or take a shortcut from one area to another. Controlling access prevents theft. It can also improve personal security. With electronic systems, each time you enter and leave, a record is retained, or some areas are locked to all access at certain hours. There is more than one type of lab security. Select the icons to learn more.
Physical security. Access to buildings and rooms is controlled by doors and locks and regulated by authorization procedures established by the Facilities Department, Security, or Campus Police. Diversion is a term used by law enforcement to describe the intentional removal and misuse of a hazardous material for a criminal purpose. Within the lab, cabinets, refrigerators, and freezers are locked to protect individual sensitive items. Please do not modify equipment. Purchase equipment that has lockable mechanisms. Computer security. Data systems are protected by active and passive measures to limit access to electronic information using passwords, firewalls, and multi-authentication methods. Situational security. Situational security is predicated on human behavior and the ability to recognize and report potential problems. It requires an awareness of behaviors that may be threatening or criminal. Examples may include anger, lack of impulse control, substance abuse, secretive behavior, ordering unauthorized materials, unusual work hours, inappropriate social media postings, despondency, or changes in personality, productivity, or cooperation. External threats may involve abusive relationships, criminal and/or terrorist intent. Always report inappropriate behavior. This will be discussed in detail.
Finally, theft of computers, personal items, and money is an unfortunate occurrence. Furthermore, experimental, patented, or pre-patented data, medical record-related data, and other sensitive data have become desirable targets for theft. Remember to lock laboratory doors, even if you have to leave the lab suddenly. Secure your personal items in a locked desk drawer. Theft is often based on opportunity. Keeping things locked when unattended removes this temptation. Follow these basic guidelines of protecting what should be secured in the lab. 1. Access is restricted to authorized personnel only. 2. Visitors are escorted at all times, never left alone, and not permitted access to areas containing hazardous materials. 3. The laboratory is locked when unoccupied. 4. To help prevent diversion of sensitive hazardous materials, access to acutely toxic chemicals and certain biological and radioactive materials requires additional locked security within the laboratory. For example, a locked cabinet, refrigerator, or freezer. 5. Physical security with hazardous materials is most effective when combined with inventory control to reconcile what is on hand, in use, and considered waste. Date, time, initials, and amount withdrawn or remaining are essential pieces of information to record. 6. Card key access systems provide security, access, and personnel accountability. These systems are increasingly common in laboratory design. 7. Emergency phone numbers are posted near every phone, and personnel are encouraged to add this information to their mobile devices. Contact your public safety department for assistance in conducting a security assessment of your laboratory. Obtain and follow your institutional computer and data security policies. The following are general laboratory safety best practices. Maintain an inventory of safety-sensitive items, biological, chemical, or radioactive, in the lab and review it regularly. Keep your laboratory locked when unoccupied. Report all suspicious activity and persons, suspected theft, and questionable behavior to your supervisor, or, if threatening, to the authorities immediately. Finally, discuss laboratory security with all new personnel and as part of the laboratory safety discussions during staff meetings.
You work in an open lab space shared by 4 lab groups. The lab covers an entire floor. Unfortunately, not everyone is easy to work with, and there is often tension and competition for equipment and space. One morning, you find that a locked cabinet used to store powerful neurotoxins was left open. What should you do? Select.
Science can be demanding and stressful, often with emotional highs and lows. When things are going well, science can be exhilarating. Yet, when things are not going so well, it can be frustrating and sometimes quite discouraging for long periods of time. Fortunately, the importance of physical health, mental health, and emotional well-being is better understood. Today, there is less stigma associated with seeking help, and institutions have expanded their counseling services. If you are having a difficult time and it has become more than just a bad day in the lab, seek help through your campus counseling programs. If you are worried about a colleague, discuss it with your supervisor in private. Experience has demonstrated that seeking help sooner rather than later is the key to getting the support you or someone else needs. Employee assistance programs, student health, human resources, and student life can all provide assistance if it is needed.
You begin to notice changes in the work habits and mood of a colleague. He's coming in late and staying well after everyone else has left the lab. Usually open and forthcoming about his work, he is missing key deadlines and making excuses for his lack of productivity. He also seems distracted and irritated over small issues. What should you do?
The issue is not if an emergency will occur, but when it will happen. Time spent preparing for emergencies, both large and small, improves laboratory safety day to day by focusing your attention on what you need when something does happen. Periodic review and practice provides you more time to refine and improve your preparations. Adequate preparation lessens the impact of emergencies and allows for faster recovery after it happens. Plan, prepare, protect, and practice provides peace of mind. Let's look at some examples of how it works. A sustained power outage, major fire, or other catastrophic event can lead to the irreplaceable loss of research materials and information. Each individual laboratory is responsible for planning for and identifying potential losses and taking reasonable precautions to protect the work. A fire, medical, or police-related event is immediate, requiring a predictable and quick response. Prepare by posting emergency numbers by every phone in your lab and enter them in your mobile device. Catastrophic events, such as a storm or earthquake, require advanced planning and preparation to lessen the impact and improve recovery. Understand that you may not be able to return to the lab for some time. On the other hand, you may be forced to stay in your lab or office. Your disaster plan should include preparations for this event also. The integration of emergency response with allied functions like crisis management, disaster, and business recovery is known as business continuity. Ensure your emergency planning efforts fit within the business continuity framework of your institution. Register your email and mobile phone number with Campus Emergency Response in order to follow their instructions in case of emergency. Develop and maintain a phone and email list that allows communication with coworkers quickly, regardless of location. Keep it current. Ensure you have a consistent, ongoing process to protect and preserve your valuable research samples and associated data. Document your efforts with written procedures. Follow all institutional guidelines on data security and the retention of important records. Together with your lab group, discuss, evaluate, and document your emergency planning efforts at least once a year. Every 6 months is better. You could do this as part of a lab meeting. See the reference section of this course for more detailed suggestions on how to better protect your research investment. It also provides valuable information on emergency planning at home. Here are some practical steps to follow in an immediate evacuation event. Identify at least 2 ways out of the building from each laboratory location. Agree on a common meeting location outside and well away from the building. Appoint a primary and secondary person to help account for everyone present that day. Ensure there is a well-understood plan in place to assist those that may need assistance in an evacuation. Finally, ensure your emergency planning is consistent with the institution's plan, and ask for help if you are uncertain for any reason. Experience demonstrates that a quick, calm, and well-communicated 911 emergency call significantly improves the response, lessens the impact, and summons the help needed. In an emergency, take action immediately. Call out to everyone around you that something has happened and ask someone to call for help. When others are there to help, each person can play an important role. You or a coworker must place a 911 call as quickly as possible, ideally within the first 2 minutes of a real or perceived emergency. If you are unsure if it is an actual emergency but sense something bad has happened, make the call for help anyway. As any firefighter or police officer will tell you, it is better to respond to a reported emergency and then determine it was not an emergency than it is to get the call late and face an emergency that has become much worse. Click each step to learn the guiding steps to follow when placing an emergency call.
Quickly but safely assess the type of emergency. Call 911 from a safe location. Emergency operators will ask you a series of questions to determine how to respond based on the information you provide. Speak slowly and clearly. For the emergency operator, the first challenge they face is pinpointing the location of the emergency. Describe the type of emergency: fire, medical, or police, its location, building, floor, room, etc., and any extenuating circumstances, for example, if you're trapped by a fire, multiple injuries, etc. They will ask your name, phone number, and for you to provide any additional details. Follow any specific instructions you are given. If you do not understand, ask or repeat what you are told. Always remain on the line until told to hang up by the emergency operator. If someone is injured in the lab, clearly state and then restate where you will meet the first responders outside the building to guide them to the injured person.
Avoid the temptation to investigate potentially dangerous events. If you see smoke or flames, never open a door to see what is going on. Closed doors provide important protection. They help prevent the movement of smoke, flames, and/or toxic vapors. Evacuate the area and wait for the emergency responders. Life safety is the most important consideration in any emergency. Property and equipment can be replaced. You and your colleagues cannot. There are certain situations where you must evacuate your building. The most common evacuation is required during a fire alarm. In the event of a fire alarm, immediately stop what you are doing. Shut off any open flames and any dangerous equipment or experiments. If you can do so safely, secure any hazardous materials before you leave. Ensure everyone else leaves with you. Close all doors behind you to limit the movement of smoke and flames and walk calmly to the nearest exit. Avoid using elevators and wait outside at your designated meeting location. Be ready to account for everyone who is in the lab that day. Again, close all doors behind you as you exit the building to limit the movement of smoke and flames. And use the stairs to evacuate. By law, you must evacuate whenever there is a fire alarm. Failure to do so is illegal, and local authorities can arrest and prosecute individuals who put first responders at risk. If you see smoke or flames, inform everyone in the area and immediately leave the lab. You can work alone or with coworkers to follow CARE. Contain the fire by closing all doors to the area. This limits the movement of smoke and flames. Activate the nearest fire alarm pull station. Pull stations are located near exits leading out of the building. You do not need to activate the closest alarm. Report the fire from a safe location. Provide as much information as you can to the dispatch operator. In most situations, it is best to evacuate the area and allow emergency services to respond. If your lab has sprinklers, these will activate to help control or extinguish the fire. You may only use a fire extinguisher if you are properly trained, you have the proper extinguisher for the fire you are fighting, everyone has left the area, you have contained the fire by closing all doors to the area, you have activated the alarm and called 911, and you have a clear exit behind you. If you cannot control the fire within 30 seconds, abandon your effort and contain the fire by closing all doors to the area. Evacuate and wait for emergency services. Never attempt to use an extinguisher if the fire has left its source of origin. In high-rise or multi-story buildings, the fire reporting procedure may differ. Please ensure you and every member of your lab group knows your specific procedure. Fire extinguishers are limited-use devices intended for a small fire that is not spread. When offered, take a hands-on fire extinguisher course. The experience of handling a fire extinguisher, especially for the first time, gives you confidence and an appreciation of its limits. The reference library contains a short video on fire extinguisher training. Chemical spills are a simple fact of life in a research lab. Before attempting any cleanup, be sure it is within your ability to manage and control. Also, make sure that the cleanup is in accordance with your institution's guidelines, and contact your safety department if you are not sure. In any case, have a spill kit readily accessible in your lab that is appropriate for the chemicals in use, and be sure to wear the proper PPE. Select the hotspots to learn more.
When handling hazardous chemicals, always work inside a properly certified laboratory fume hood. If you spill something, it is safely isolated and contained, which provides protection and time to plan your cleanup. Check the SDS for the chemical to obtain information on how to clean up the spill safely. For small routine spills that do not pose significant risk to health or safety, a chemical spill kit can be used. Spill kits are used to contain and absorb spilled liquids. A typical spill kit includes absorbent materials such as absorbent pads or towels, clear plastic bags, waste labels, and ties. Used absorbents are bagged, labeled, and set aside for disposal as hazardous waste. Bag contaminated gloves, labware, and other spill debris as well. If the spill involves hazardous materials that are outside of the laboratory fume hood and pose a health and safety risk, leave the area and call your safety program for help. Prevent others from entering the area until properly managed. In the event of an acute chemical exposure, or if there is a potential for fire because of the spill, call 911 immediately.
Select the hotspots to learn more about chemical contamination emergencies.
Nose or mouth. In the event of inhalation exposure, relocate the victim to fresh air and dial 911. Eyes. In the event of contact with eyes or skin, go to the nearest eye wash station, sink, or safety shower. Flush the affected eyes or skin while removing any contaminated clothing. Ask a coworker to call 911 and continue flushing until help arrives. Protect yourself by wearing PPE.
Laboratory security, personal well-being, and emergency preparedness are essential aspects of laboratory safety. Planning for and addressing these concerns is an ongoing responsibility. Without planning and preparation, the impact of security lapses and the potential harm to you and others could come at a high price. Thoughtful planning, early intervention, protection of the lab, individuals, and processes, as well as practice of these safety procedures, are essential in reducing the impact, obtaining help, and recovering sooner. The best time to prepare for emergencies is well before they happen. However, despite the best preparation, if you are hurt or injured or become ill in the laboratory, promptly notify your supervisor, health and safety program, or risk management office. Complete an accident injury report. This formal record helps to protect you and your institution.
A colleague working in a laboratory fume hood on your side of the lab just set up an experiment and stepped away. Without warning, there's a loud bang. The sash of the fume hood shatters and a fire erupts, spilling out into the lab. The fire spreads quickly, producing large amounts of smoke. You're understandably startled but not hurt. What are the correct actions you should take now? Your lab works with corrosives, both acids and bases, in varying concentrations. This afternoon, a student combined 2 incompatible corrosives into a single container on the bench. The resulting violent reaction creates an excessive heat and highly corrosive vapors. This reaction also sprays the student with the chemicals. Fortunately, she is wearing all the assigned PPE, but nevertheless she seems severely hurt. What is the correct sequence of priorities to follow to manage this emergency? First, assess
Report any injury, illness, or incident to your supervisor and health and safety office as soon as possible. Also report unsafe situations to your supervisor and health and safety office. Reporting is a positive step toward prevention. Severe injuries or hospitalization must be reported to your supervisor and health and safety program within 8 hours. By law, serious events must be reported to your state or federal safety and health administration. Employees are covered by workers' compensation. Your risk management and insurance office will have forms to cover your expenses. Near-miss events are those that don't result in injury or damage to your lab. If your institution has a near-miss reporting system, please participate. Reporting near-miss events can help prevent a similar event in the future. In this section, we discussed laboratory security and emergency planning and response. In summary, please remember to plan, prepare, protect, and practice. Keep your laboratory secure to prevent theft. Lock the doors when the lab is unoccupied. Back up your computer and take precautions to protect valuable samples. Plan and prepare for emergencies. Discuss emergency procedures during your lab meetings. The better prepared your lab is, the quicker you can respond, lessen the negative impact, and return to normal operations. Finally, be prepared to take care of yourself at home for at least 72 hours after an emergency.
In case of emergency, contact UC Davis Environmental Health and Safety. Click on the image below to access the UC Davis Injury and Illness Prevention Program. Click on the image below to access the UC Davis Chemical Hygiene Plan. Click the image below to access the UC Davis Hazard Communication Program. For more information, contact Environmental Health and Safety. When you are ready, click Take Test to begin the assessment. That is correct. Cold temperatures associated with the use of cryo. That is correct.
Fume hoods are one of the most important safety features in a research laboratory. The hood is used to protect researchers from breathing hazardous airborne chemicals, and the sash can be used for protective shielding. This presentation demonstrates how to use your fume hood properly to better protect yourself and our environment from exposure to hazardous materials. When you use the hood, you should turn on the hood light so you can see clearly. Check the hood certification sticker. It will list the date Facilities Management last checked the hood, the average inflow, and whether the airflow was satisfactory. One should always check the quantitative airflow monitor or alarm to verify that airflow for the fume hood is proper. There are several types of airflow monitors used on campus fume hoods. For this video, we will show you a few of those common types. Digital monitors display air velocity into the hood and should read more than 100 feet per minute. Some monitors will only display red, yellow, and green indicator lights. All monitors have an audible low flow alarm. Some fume hoods have differential pressure monitors that look like this. Since these monitors may be different from building to building, check with your supervisor for the correct meter reading. It should always be greater than 0. If the hood airflow monitor indicates low airflow, first try lowering your sash. If this does not resolve the alarm, contact your Department Safety Coordinator, EH&S, or Facilities Management for maintenance. Adjust the sash to the proper height. In this case, the glass sash was raised to the maximum working height as indicated by the joined arrow, and then slightly lowered. The tissue on the sash is drawn in, indicating that there is airflow into the hood. Most fume hoods now have this label on the sash frame. Be sure to use the sash in the green zone as much as possible. A sash should only be in the red zone for equipment setup. When you are finished with your work, be sure to lower the sash and save energy and protect lab occupants. Airflow turbulence at the front edge of the hood can draw airborne contaminants out of the hood. In this case, the sash is too high, and when someone walks by, the low inflow velocity allows the smoke to come out of the fume hood. Sashes properly adjusted and working further into the hood are the best way to protect yourself from inhaling hazardous chemicals used in the hood. Move extra equipment out of your way and always work at least 6 inches from the front of the hood. Some hoods have a combination sash that can be opened horizontally or vertically. In this case, the sash is lowered, then the horizontal sash is adjusted to provide protection from explosive reactions or chemical splashes. In older buildings, fume hoods may have horizontal sliding sashes and a velocity screen to meet the 100 feet per minute inward face velocity. Horizontal sashes need to be placed in front of the work and the velocity screen lowered to maintain a safe working environment. Typically, there are no pollution control devices on fume hoods. The airborne contaminants made in a laboratory hood are exhausted from the roof stack into the environment. Never evaporate chemical waste through a hood, and when working with a hood, minimize the volatiles released to protect our air quality. When you are done using volatile chemicals, close and seal the container. When finished using the hood, close the sash and turn off the light for added safety and to save energy. In review, before using the hood, check the airflow monitor. Properly adjust the sash height for your work. Always work at least 6 inches from the front of the hood. Fume hoods exhaust into the environment. Minimize your fume hood emissions. Close the sash when you are done working in the hood. In closing, if you have questions about your fume hood, ask your lab manager, Department Safety Coordinator, or contact the Office of Environmental Health and Safety. Also, read the Fume Hood Safety Net and other laboratory safety information available at the EH&S website.
Too many objects inside a laboratory fume hood can disrupt the airflow and possibly compromise your safety. Which of the following are considered best practices in the use of a laboratory fume hood?
Are done.